All right, so moving on from the first part of chapter 1, where we talked about significant figures and scientific notation, we're ready to start to add another piece of information to the numbers that we've looked at so far and start to use units to describe what those numbers actually mean in terms of the physical system or the problem that we're looking at. So when we make that measurement and we get a number, there's also going to be a unit attached to it that describes it. The units that we tend to use in chemistry as well as in all of the sciences are based on the metric system. So you may have a little familiarity with the metric system, but we'll go into some of the basics and some of the things I would expect you to know if we have an exam as we go through this set of notes. The metric system is part of a larger system that's used in science called the International System of Units, or in short, SI units. So SI comes from the French version of the phrase Système International, where this idea originated. So we want to be familiar with the units that science tends to use, because that's generally what we're going to use when reporting on a specific topic in terms of length, time, volume, that sort of thing. So some of the things we might want to measure in lab that we might need the units that go along with, I have listed here. So we'll go through a few of those. If we're measuring length, the SI unit for length is the meter, right? Meter, of course, is the basics of the metric system. Meter is pretty long, particularly for use in a chemical laboratory experiment, for instance. So it's fairly common to put a prefix at the front of any particular unit to divide it into smaller pieces or to multiply it into larger pieces. Centi at the front of the word here, a centimeter, means 1/100th of a meter. So a centimeter is a much smaller measurement of length, and 100 centimeters would be equal to 1 meter. Now, in terms of US units, the centimeter is reasonably close to the measurement of distance, the inch, that we use in the English system. So 1 inch is equal to 2.54 centimeters, so about 2.5 centimeters per inch. Volume, another quantity we might want to measure. The SI unit is the liter. Most folks are fairly familiar with the liter from soft drink bottles. The 2-liter bottle is pretty standard in the United States. A liter, again, that's a lot of liquid for doing a laboratory experiment, so it's very common to add another prefix here when we're using volume units, and that prefix is milli, which means 1,000th. So a milliliter is 1,000th of a liter, right? Or 1,000 milliliters is equal to 1 liter. So put that milli at the front, we get the abbreviation M there. For milliliter is a version we will commonly use. Mass is another quantity we might want to measure. The SI unit for mass is the gram. Now, gram's a fairly small amount of mass, so that's the one that we will generally use in the laboratory. If we're measuring other things outside of the laboratory, like humans, for instance, gram is very small. So might be a little discouraging if you weighed 100,000 grams when you went in for your physical and had to step on the scale at the doctor's office. So if we add a prefix kilo, this means 1,000. So a kilogram here is a larger unit than a gram. In fact, it's 1,000 times bigger. So there are 1,000 grams in 1 kilogram. So someone who weighed 100 kilograms would weigh 100,000 grams, right? 100 kilograms sounds a little bit better in terms of how much you weigh and maybe whether you're allowed to eat some cheese or something like that. All right, moving on to another page here. Temperature falls outside of the metric system, but temperature is something we will certainly need to measure as we move through some of the things we're going to discuss this semester. And one of the things we'll focus on when we get to the chapter where we start to talk more about heat and the movement of heat is the conversion between different temperature scales. So I've got conversions listed here as something we should think about. I'm not going to talk about the conversions just yet because that'll be more relevant when we are using temperature more intimately in our calculations. So for now, I just want to point out there's really 3 competing temperature scales. Got a big glob of cat hair on the page there. Sorry about that. Fahrenheit is the scale we usually use in the United States, so degrees F is degrees Fahrenheit. Celsius is the temperature scale that's used around most of the rest of the world, so degrees C here is for the Celsius temperature scale. But in science, we often will want a temperature scale that we can use in a calculation. And that means it can be difficult in a calculation to deal with the fact that the Celsius and the Fahrenheit temperature scales change from positive to negative, because it's hard to design an equation that will factor in that, say, -5 has a lower temperature than +5 in your calculation. So the K here stands for the Kelvin scale, and in Kelvin is closely related to the Celsius temperature scale. It's just shifted. And it's shifted in a fashion where the lowest possible temperature would fall at 0 in that scale. So there's an idea called absolute zero, which being you've removed all the energy from a system and there are no longer vibrations in that molecular structure. That would correspond to 0 Kelvin. Any other temperature would be positive relative to that temperature of 0. So in that sense, when we're going to do a calculation, we need to plug in directly the temperature. We can plug in that Kelvin temperature and it'll be a positive number, and we don't have to worry about dealing with that change to negative in there. Time is another quantity that we will often measure in a calculation. The SI unit for time is the second. I think most of us are fairly familiar with time units. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, etc. So what time unit we use does depend on the length of time that it takes for a particular process. Right? If we're talking about something like the radioactive decay of uranium, that's going to be something that happens over billions of years. So seconds does not become a particularly good way to describe that process. So we will switch that time unit up to one that more matches what we're describing. A lot of reactions, though, happen very quickly, in which case we will probably talk about seconds a lot. Okay, now we've got a basic unit. I mentioned a few examples of metric prefixes where we can alter the size of the unit we're using to make it either a larger quantity if we're measuring a lot of material, or a smaller quantity if we're measuring a smaller amount of material. So I just have a few of those units listed here. Kilo we saw is 1,000. If we go even bigger, there's mega, giga, right? And in fact, if you follow computers, you may have heard of tera. Like a teraflop of data is even bigger than giga, which is a billion. So a giga meter, for instance, would be 1 billion meters. The only one that's fairly common in chemistry is the kilo. Kilo is often used to indicate 1,000 of something, so not just kilometer, kilogram, but things like kilojoules. A joule is an amount of heat, but a joule is a fairly small amount of heat, so we often want to make that bigger and use kilo. So I'm putting a mark around the ones that I would expect you to know on a test. So if we get to the point where we're doing a conversion and you need to convert, say, from meters to kilometers, I will not tell you what that relationship is. I expect you to know that one. In terms of smaller, I've got a few here. Deci is 1/10, centi is 100th, milli is 1,000th. And we saw milli back in the comparison between liters and milliliters. Milli is one that's very common in chemistry as well. So that's also one I would expect you to know. Depending on how far you go taking chemistry classes, micro, nano do become a lot more common, depending on the field you get into. But in terms of what we're going to do in Gen Chem, we just don't encounter them that often. So if, for instance, we do a conversion and your answer should be in micro liters, I will give you the conversion for that particular calculation. But you should know kilo and milli when we get around to a test. Now, really, anything else, if you're doing practice problems outside of class, you can find that information in a table to get the right prefix that you're looking for. Okay, so now that we have a little bit of an idea about putting units and associating them with our numbers, we want to look a little bit at how we're going to use the units. The units will be kind of the basics of a problem-solving technique that we'll use for lots of the problems we're going to encounter through this semester. And this technique is based on the idea of setting quantities equal to each other, or equalities. So I have a few listed here, right? We could say a dozen eggs is equal to 12 eggs, right? Both quantities on the different sides of the equal sign are the same there. That's kind of what equals means, right? In length units, 1 meter is equal to 100 centimeters, for example. Volume units, a cubic centimeter is equal to a milliliter, right? And a cubic centimeter is also abbreviated sometimes as cc, particularly in medicine, pharmacy sort of applications. But those are all the same amount of material in terms of volume, so they are equal to each other. And in terms of mass, 1 kilogram is equal to 1,000 grams. Now, what we want to look at next is how can we take information like this in the form of an equality and use it as a tool to solve problems. And that's what we'll do in the next video.